Hi, my name is Rakshit Solanki. I'm an Inside Data Engineering Fellow in Silicon Valley, 2K19. I built a project during my fellowship. Name is UMatch. I try and build a special scenario in maximal bipartite matching in graph theory, a greedy bipartite matching. Now, let's imagine you are launching a startup just like Uber. So your your organization will need an algorithm to match your drivers and the riders in a real-time streaming window. Now, one may argue that Uber already has an algorithm, so why you need to build another one? So my answer is Uber's algorithm is not open source. They don't share any information on implementation of the algorithm in the community. So that's the first one. And the second one is if we look at the graph problem matching, if we have two disjoint set of vertices and if we want to find a maximal matching between them, then that is called maximal bipartite matching in theoretical computer science. I initially thought to build a maximal bipartite matching on my two disjoint set of vertices, which is drivers and the riders. Then I started looking at few of the stream processing engines graph processing library, which is one of them is Flink Jelly, which works on top of Flink and Spark graphics. But both of these libraries are Google Pregal model based, which means that it only works for batch processing environment. That means if you want to process a graph in a batch environment, then it is the best solution to that library. One of the other library is Apache Giraffe. That also does graph computation batch environment very optimistically. But that was not a solution because I wanted to build my scenario was to build a matching in a real-time environment. So then I look at graph database like Neo4j. But if I use Neo4j, then due to my velocity of drivers and riders which is coming into my data pipeline, then Neo4j will encounter a lot of latency of writes and access. So that's why it was not an optimal solution for me too. So then in the 3 weeks, I figure out one of the optimal solution, one of the workable solution. I would not say it is optimal, but it is workable for the first iteration of any of the organization. So it goes like this: that if I have two streams, drivers and the riders, if I take a snapshot of 2 seconds or 5 second window on those streams, and I join the two windows using left outer join, and after I get the join results, I do a greedy matching uh, on those join results, then the results I will get will not be as optimal as maximal bipartite matching, but it will be workable for the first iteration of any organization. So looking that into mind, I started building my entire infrastructure. So my data pipelines architecture look like this. This entire infrastructure is built on AWS. I used 6 nodes Spark cluster and 2 nodes Kafka cluster for building this entire pipeline. Now my data sits in Amazon S3. I'm using NYC Taxi rights dataset, which is AWS open dataset. You can access it any which way you want from AWS S3. I'm streaming my data from S3 to Kafka just to make sure that my data pipeline has exactly once processing semantics and none of the riders and the drivers got lost in the processing. Then up from Kafka, I'm creating a DStream to Spark using Spark streaming. My Spark will do joins, aggregations, and transformation, and it will apply the match algorithm, and then it will compute the statistics of match, and then it will sync back the results to Kafka. Now, I didn't include any persistence layer database in in the entire pipeline because uh, accessing the data from the database won't be an issue if I use columnar dataset database but inserting the data will be a issue. It will cause a latency because my velocity of data like rider request and the driver request are very high. So that's why it will create a latency. That's why I didn't include any database layer. So that's why I'm syncing my data to Kafka, and then from Kafka I'm directly visualizing my data uh, using Spring Boot, Charges, and WebSocket. So now let's look at the demo. I already has the demo started. So let's look at that. So this is my entire demo. I created two graphs because I had only 3 weeks time to build this entire data pipeline and the UI. I only managed to compute only one matching statistics, which is total number of riders, total number of match, and total number of drivers, and how many of them are matched with the riders. Only these statistics I could able to compute in short time span of 3 weeks. So let's look at the graph. I have two graphs, which is line graphs. On x-axis, you can see the time, and on y-axis, you can see the match. On the y-axis, you can see the numbers. If you hover over the graph, you can see how many riders came in that particular window and how many of them were matched. So, for example, in this particular window, 3,000 riders came in, and out of them, 2,500 were matched. So the results right now, the matching results are not optimistic because uh, let's face it, it is not optimal algorithm, but there is some match statistics. It can be workable solution for the first iteration. I would not say to productionalize it, but it can be a workable solution. So if we look at the second graph, it is also the same. In the red, you can see the total number of drivers, and in the blue, you can see how many of them are matched in that particular window. Let's get back to the presentation. I would like to walk you through a few of the engineering challenges I faced during building this data pipeline. So the first sort of challenge I faced is I'm using NYC Taxi rides dataset, which contains completed trips in New York City. Uh, some of the there are a lot of CSV files and JSON files, but some of them doesn't contain few of the attribute information. For let's say driver's location is not at all present in entire 260 GB data set. So I need to create a synthetic driver's current location, and there are few of the data in my streaming which is synthetic, such as I'm generating synthetic records for driver request between the pickup point and the drop off point of one particular ride. Like I am generating 100 different points of rider pickup location, and for the drivers too, I am generating random synthetic data of driver's location with particular driver ID. So after creating these two streams, the second challenge was to join the two streams. I know there are attributes like driver ID, pickup ID, drop-off ID, a drop-off location, and the timestamp. And the driver's window has driver's ID, driver's location, and the timestamp. But there is no common key except time to join these two streams. But if I join on the time, then the results I get after joining will not be optimistic, I would say, because it will only match drivers and the riders at time t, but I want the results of match at time t0 and time t1 too. So that wouldn't be a optimal solution for my case. So then the obvious solution is to do Cartesian join of entire window. That means my each rider request will be joined with all the drivers in my streaming window. So that will add a lot of data in my RDD. So after joining it using a Cartesian join, my RDD will contain n square records, where n is number of data present in RDD, driver RDD and the rider RDD. And after that, creating one single RDD of join, then on that particular RDD, I'm applying my greedy match algorithm using Harvard's and distance. But I implemented this code. I ran it in my pipeline, but Spark was taking so long to compute the entire RDD and matching distance. So I discarded this idea. Uh, then finally I came up with my algorithm, which is some way optimistic in terms of finding the matching. I have to so algorithm goes like this. I have two data streams, rider stream and the driver stream, uh, and I'm creating first geolocation hash on rider's pickup location and the driver's current location. The geolocation hash is 5 decimal points. So if you look at longitude and latitude, all the numbers after decimal point represent the radius on actual map. So 5 decimal point represent around 10 kilometers radius. I'm not sure though. I have I don't know exact number, but it represent around 10 kilometers of radius. Uh, After creating a geolocation hash, I'm assigning that hash as a RDD key value, key, and all the other parts as a value. So in my case, if you can see in the orange box, that hash is as part of key, and all the other are values. And then I'm joining the two RDDs using left outer join. So after joining, it will create small buckets. That means my search space for matching will be reduced. That means all the drivers and the riders which falls under 10-kilometer radius will be present in one bucket, and there will be multiple buckets of this kind based on the locations, based on the radius. And then I'm applying my matching algorithm to all these particular buckets. And after all the buckets are matched, or all the records in the buckets are matched or not matched, we have the results. Then I'm merging those results and syncing it back to Kafka. So that's all I would like to say a bit about me. My name is Rakshit Solanki. As you know, I'm a recent graduate from California State University, Fullerton. I am open source enthusiast. I really like to work on open source projects, learn them, and try to contribute to them. I would like to give an example of uh, recent example that when I started building this pipeline, I wanted to utilize Kafka graphs library. Right now, Kafka doesn't support graph computations, but there is one open source repository on GitHub which has implemented graph algorithms using Google Pregel model. Uh, there are only few algorithms available right now. So I talked with the owner. I asked him if I wanted to implement this kind of matching solution using bipartite matching, if I can contribute that algorithm. Going forward in the discussion, I realized that this is not a best case solution for my project, but any which way I'm working on the solution of building graph problem maximal bipartite matching on Kafka graphs. So yeah, that's all about me. Going forward, I'd like to be successful data engineer. Thanks.